Lecture 35 of Physics 72 discusses sinusoidal EM waves. We utilize the mathematical descriptions of mechanical waves from Physics 71 in understanding more about oscillations of plane electromagnetic waves. We only have one objective for this short lecture. Given a solution to the wave equation, we need to identify different properties such as wavelength, wave number, frequency, and directions of important vectors E, B, and propagation V. Lecture 35 discusses Chapter 32.3 of University Physics. This will be the last sub-chapter covered before we fully transition to the topic of optics. Recall that plane electromagnetic waves consist of electric and magnetic fields oscillating perpendicular to the direction of propagation. This graphic visualizes the oscillations of E and B, E being the red wave and B being the blue wave, as the wave travels to the right. Okay? So if we try to focus on just one of the waves, notice that they look very similar to the traveling waves that we've encountered in our mechanics lesson in Physics 71. Well, it turns out that they have almost identical equations, so it's worth going back to discussing wave functions. Now, we lightly touched on the wave differential equation, which is given by partial squared y over partial x squared is equal to 1 over v squared partial squared y over partial t squared. So our wave function, let's call it y for now, so that it's more consistent with our lessons back in Physics 71. And the solution for this differential equation is a traveling wave. And we call this wave function y. And this is a function of position and time, and is given by a cosine kx minus omega t. Now you could also use sine, but then it's up to you. It depends on the initial conditions. A here is the amplitude of the wave. K is the wave number, which is equal to 2 pi over lambda. And then omega is the angular frequency, which is something that's already well known to us. It's given by 2 pi f. The arguments of the cosine function should be dimensionless, so we know that x and lambda should cancel each other out, and then omega and t should cancel each other out. The minus sign next to the second term of the cosine argument indicates that this wave is traveling in the positive x direction, and the function's dependency on x means that it is traveling in the positive x direction as well. Okay. The slide shows two wave functions that satisfy the wave differential equation, but then there is a slight difference in the argument, and this distinguishes how the wave travels. You can see the graphic on the left shows two waves. The one on top is, well, looks like it's traveling to the right, and the one on the left, the one at the bottom, looks like it's traveling on the left. And while these two equations, or these two waves, will have very similar equations, there's one distinction, or there's one difference that basically tells you which way the wave should go. If the second term is subtracted from the first, and this is what we're looking at the argument of the cosine already. If the second term is subtracted from the first, then the wave will travel in the positive x direction. So in this case, it's going to point here. But then if your argument or arguments in the cosine function are positive, you're going to end up with waves traveling in the negative x direction. So all of this has already, or all of what I've said so far have already been discussed in Physics 71. And our goal for today, or for this lesson, is for us to transition what we know from wave mechanics and use them for electromagnetic waves. As I said a while ago, we now try to connect this wave function concept to electromagnetic waves. Our focus from last session was on planar electromagnetic waves, which means that our wave fronts, or how our wave travels, is based on flat planes, and these waves oscillate sinusoidally. And as with last session, we have an electromagnetic wave traveling in the positive x direction, as seen in the graphic on the left. So the velocity c points in positive x. And our electric field is polarized in the y direction, and this means that if you follow the right-hand rule, B should oscillate in Z. And as these planar waves oscillate sinusoidally, we expect field components EY and BZ to take on forms similar to our wave function from the previous slide. The electric field component EY should be equal to Emax cosine kx minus omega t, and then the magnetic field component BZ is equal to Bmax cosine kx minus omega t. Emax and Bmax are the magnitudes of the waves E and B respectively. So take note that the components are chosen, so Y for E and Z for B, and they're based on how the electromagnetic wave was oriented. So we assume that there's no component of electric field in Z, and then there's no component of magnetic field in Y. Now in the vector form, we take E to be equal to J hat, E max cosine kx minus omega t. And then for magnetic field, we have K hat, B max cosine kx minus omega t. Now, consistent with the components, E is parallel to J hat because, again, we're looking at EY, while B is parallel to K hat because it's only in the Z direction. Note that the orientation of the field cannot be the same as the propagation direction, or in this case, our direction for propagation is X. This is because the electromagnetic wave that will satisfy Maxwell's equations should be transverse waves. And from the previous lesson, we said that the oscillation of E and B should not have a component in the same direction as the propagation. Here is an animation showing the electromagnetic wave traveling in the x direction, or positive x direction. The electric field in red is oscillating in y, and it looks like a traveling wave. The same can be said about the magnetic field, with the difference being that B oscillates in Z. We said that these plane sinusoidal waves share similar forms with the mechanical wave function. And looking at the expressions for the components, we see that Emax and Bmax are the magnitudes, K is still the wave number, and omega is still the angular frequency. The likeliness is easy to see since they share almost the same forms. We can relate magnitudes Emax and Bmax with Emax is equal to C times Bmax. And note that this equation was already obtained from the condition needed for electromagnetic waves to satisfy Faraday's law. That was from the previous lesson. We also take note that because the arguments of the cosine functions of both components have subtracted second terms, the omega t's, we agree that with the diagram, that this electromagnetic wave is traveling in the positive x direction. In vector form, E is equal to J hat times EY, and B is equal to K hat times BZ. In classifying how the electromagnetic wave is oriented, it is enough to look at the polarization of the electric field, or basically how it's oriented. In this case, it is linearly polarized along the y-axis. Looking at the speed of the wave in vacuum, we get C, which is already equal to lambda f. We get a new relationship for it. It's defined by the ratio omega over k, which is also equal to 1 over square root of epsilon naught mu naught. You can check for yourself that after canceling the 2 pi factors, you will recover the lambda frequency expression if you divide omega by k. So that's going to be f divided by 1 over lambda, which is what you'll get eventually from here again. What if we want to see how the wave function changes if we want it to propagate in the other direction, or negative x? Remember that the direction of propagation can be reversed with a simple change of sign in the argument of the trig function. E and B would still be oriented along the y and z axis respectively, but some changes in sign must be applied. For E, a change in sign in the argument of the cosine function is sufficient. So it becomes plus omega t instead of minus omega t. The same change must be done for B, but we have to change its amplitude factor as well, from Bmax to negative Bmax. From this, we arrive at the expressions for plane EM waves traveling in the negative x direction. The peculiar negative sign in the magnitude of Bz arises from the fact that the magnetic field amplitude should point at negative k hat to maintain the cyclic permutation of E, B, and the wave velocity. Note that E cross B should be parallel to C. When E is oriented in the plus y direction, B must be oriented in the negative z direction to get a cross product result parallel to negative I hat. Alternately, we could choose E to be oriented along the negative j hat direction if you want B to be the one with the positive amplitude, or B oriented along k hat. Or either way, you get the same result, negative I hat. Let's reiterate one more detail of the electromagnetic field equations. Consider the vector equation of E polarized in the y direction, and we set the EM wave to propagate in the positive x direction, as you can see in the equation there. The oscillation direction of the waves are the unit vectors multiplied beside the trig function and the magnitude. So for this case, it's j hat. The direction of propagation is indicated based on whether omega t is added or subtracted in the function. Since we have a subtraction, we know that it's going to propagate in the positive x, and we know that's in the x direction because that's what E is dependent on. Remember that for transverse waves, the fields should not have a component oscillating in the direction of propagation. So if one asks if EZT is equal to k hat E max cosine kz plus omega t possible, or is it a possible wave function, we answer no, because k hat indicates that the field oscillates about z. But the function's cosine argument tells you that it's already propagating along positive or negative z for that matter. Field oscillation and wave propagation must be in different directions for transverse electromagnetic waves. And we want transverse electromagnetic waves because they're the ones that satisfy Gauss' law. Let's answer a few exercises to sharpen our understanding. An electromagnetic wave has an electric field given by E y of t is equal to 3.1 times 10 raised to the 5 volt over meter, that's your magnitude, k hat, times cosine ky minus 12.65 times 10 raised to the 12 radians per second t. The following questions are A, in which direction is the wave traveling? B, what is the wavelength of the wave? And C, we're asked to write the vector equation for By of t. And an important part is we assume that the light is traveling in vacuum. Now, to answer A, all we need to do is to check what positional variable is the field dependent on, as well as the argument of the trig function. In checking the argument of the cosine term, we see that the wave should propagate in the positive y direction, or plus j hat. The wavelength of the wave is determined by the wave speed equation C is equal to lambda f. Frequency f is just 12.65 times 10 raised to the 12 over 2 pi. We'll have to divide by 2 pi because 12.65 times 10 raised to the 12 is omega. Then lambda is just the ratio of C over F. We should get around 1.50 times 10 raised to the negative 4 meters. Finally, from the given, E is oriented in the positive z direction. And from A, we know that the wave is propagating in the positive y direction. This means that positive k hat cross something is equal to positive j hat. That's from E cross B equals or parallel to propagation. A simple check using the right-hand rule or cyclic permutation leads us to a magnetic field B that points in the positive x direction. We get the magnitude B max from the relationship that E is equal to C times B. So B max is just equal to E max divided by C. And from there, we just copy the cosine argument of the electric field, and then you already have your expression for the magnetic field. For the second item, we consider the magnetic field of an electromagnetic wave traveling in a medium. And this is given by Bzt is equal to B naught times J hat times sine kz plus omega t. We are asked to determine the following: the direction of propagation, the speed of propagation, and the corresponding electric field. So since no explicit values are given, we're just going to answer expressions. Looking at the argument of the sine function, we know that the EM wave is traveling in the negative z direction, so it's negative k hat. For the second item, the speed of propagation is determined by dividing omega by k, and this is already an expression that we know, so it's just a recall question. Finally, the right-hand rule indicates that E should point in the negative x direction, and its magnitude is just b naught multiplied to the wave speed from the relationship E is equal to cb. Or in this case, since you're traveling in matter, c is replaced by v. The complete electric field expression is then just equal to v b naught times negative I hat sine kz plus omega t. The last problem may be solved using similar strategies from the first two questions. Direction of propagation may be determined from the argument of the sine function. The direction of the magnetic field is determined by the right-hand rule, or through cyclic permutation. And the amplitude of the magnetic field is just obtained by the relationship E is equal to CB. I'll leave the calculations up to you. You may pause the video if you like. So this is it for lecture 35. Thank you for listening.